Swayam Prabha. Digital India. Educated India.
We saw in the last class different building blocks of microprocessors. Okay, the combination logic circuits, the sequential logic circuits, and we saw also memory and its addressing. So in this part now we'll start putting together everything to construct a microprocessor. We'll start off with some small primitive microprocessor construction, and then we will look at how these instructions are executed inside a microprocessor. Okay, so we have in the last lecture we have seen the operation of transfer of data from external register to the memory. Okay, what are the sequence of things that have to be happening for different pins that will carry out that operation. Okay, now how this operation can be done by using some kind of a timing and control circuit, we'll introduce that here, and then proceed for like introducing more and more kind of a functionality to this microprocessor, and get a glimpse of how things are happening inside. Okay, so here the idea is to kind of introduce you to the basic fundamental understanding here for the timing and control circuits, and the basics of microprocessor instruction sets and things like that, architecture, instruction sets, everything. And then based on this you will be able to understand the modern microprocessors and microcontroller datasheets in much kind of a better fashion. Okay, that's how we have introduced these lectures here. Okay, so we'll proceed with first with the example we saw in the last class. So you just recall this, that we had this sequence of operation to be performed for getting the data from the external register A now to be transferred to some memory location, where that memory location is indicated by this address which is on the address bus here, and that address is stored in this register called MA. So the sequence of operations would go something like, you need to have this output enable for MA going high, which will take the data from this register and put it on the address bus. So when the data the address bus has some kind of a data, that particular location in the memory will be addressed now, and then you want to make this enable this chip select, and this so that this particular write operation is enabled, and then we have this valid data to be there on the data bus, and then this operation this writing of this data here will be done. So how do you get the data on the data bus? To same way, like you made output enable pin high, and then the data from the register A will be now available on the data bus. Okay, so this will be captured in the timing diagram as we have seen in the last class in this kind of a fashion. Okay, so you see that here this is output enable for memory address, and then there is output enable for data register. So you know that now these are the like numbers, some kind of a sequence that is there in which the operation needs to happen. How would we get this operation done now? By some kind of a circuit or logic circuit. Okay, so we make use of some sequential logic for this. So let us understand first, suppose you have some different problem given here. Okay, so how do we generate this sequence of these pulses, which will light this bulb first, then this will light this bulb, and then like this bulb and this bulb, like that it should light in a sequence like S1, S2, S3 and S4. Okay, so they need to be on for a while, and once S1 goes off, S2 should get lit up. Okay, so that's what we want to do. So how do we do this? Okay, So if you just scratch your memory a little bit and see our sequential logic circuits which we have seen, there is one example there which will help us here. So if you recall thing and then proceed. Okay, so yeah, it is a ring counter. Okay, so this in the ring counter you introduce this sequence like 1 0 0 0. So this state is 1 here, which will have introduced, all others are 0, and then in the next clock cycle that 1 will come here, and then in the next clock cycle it will proceed here, and if you have this feedback which is coming like so this is continuously, this sequence will go on in a loop 1 0 0 0 0 1 0 0 1 0 0 0 1 0 and 0 0 0 1. It will happen for S1 S2 S3 S4 in a loop, and that's what we want for these lights to be lit up in a sequence. Okay, the timing diagram for this such kind of a case will look something of this sort. Okay, so S1 is lit up first, then S2 is lit up after that. Once S2 goes off, then S3 is lit up, and S3 goes off, S4 is lit up, and again S4 goes off, S1 is lit up again. Okay, and then this this continues in the clock. Okay, so now if you want to make use of this sequence to realize this data transfer operation for external register to the memory, that's what we are talking about. So we see the timing diagram again carefully for the operations that we want to do, and then now we put this S1 S2 S3 S4 in some kind of a time sequence here. Okay, S1 S2 S3 S4. So there are these 4 kind of timing zones which we have mapped here, and in that, like we know S1 will go high first, then S2 will go high, then S3 will go high, and then S4 will go high. This is what is going to happen in time for us now. Okay, so now how do we make use of this S1 S2 S3 S4 going high in a sequence to execute like what we want here? So remember, our inputs are this WA, CS and address bus, and output enable. Okay, so these are the inputs which we need to provide some kind of a proper signals to these inputs so that our operation happens in a way that is governed by this timing diagram. Okay, so let me get a pointer right. So now think about this. Okay, what we need to do. Okay, so this combination logic we can use on S1 S2 S3 S4 to produce this appropriate output which can be connected to this OE pin here or OE pin here or CS pin and WA pin here. Okay, that's what we want to do. Okay, so how do you think about so say if you go back and see your S1 S2 S3 S4 all 4 cycles, this address bus has valid data which is coming from making OE for the memory address to be high. Okay, so we OR these inputs S1 S2 S3 S4, they are ORed with each other to produce some output. That output will be connected to this output enable of memory address. Then all the sequence all S1 S2 S3 S4 durations, your memory address will be holding the address bus will be holding valid address. Okay, so that's how we can think about. So like that you think about for other pins what is a combination of S1 S2 S3 S4 to be used, and then proceed. So you can see now that this circuit is going to look something of this sort. Okay, so you have S2 S3 connected with OR gate here, S3 S4 connected with OR gate here, and then you see that in S2 S3 sequence you will have this will be S2 and S3 sequence, like this will be happening. S2 S3 are here, so this part will be happening. Okay, so this will be done to the chip. Okay, and S3 S4 sequence you will have this valid data here. Okay, so one can see that by using simple kind of a like that the sequence of pulses going high one after other, and some kind of a combination of these those pulses in the combination logic way, we can achieve the task that we wanted to do. Okay, so this is one of the tasks that we had. Now the question is, like, many such tasks can be performed now. One can see that easily. Okay, so we can put together many different kinds of elements, okay, as whatever we have seen, combination logic elements, adder, comparator, or this many different kind of possibilities are there, okay, and many sequential elements also can be there, and then we can put together all these to build now our microprocessor unit, okay. So how do this work with like now we'll see with the example, okay. So we want to have a microprocessor which will consist of some temporary registers, okay, and some memory. Then you can put in some combination logic circuits to do some additional addition, subtraction operation, logic output operations, okay. All those kind of things can be put together, and then we will need a timing and control circuitry, the way we had these 4 pulses coming up, similar kind of a timing and circuit to execute this desired task, okay. So we will see one with some example of actually put together this, okay. So this is a primitive microprocessor architecture that is shown here. So see, this microprocessor architecture or microcontroller architecture will typically given in such kind of a diagrams, and these different registers, there is a data bus, then the registers will have some functionality that is given in the data sheet of the microcontroller. This data bus, this kind of a thing tells you that the data from this register can be written and read also, okay. But in the register T, the data can be only given as an input. One cannot read the T register. Like that you can read this kind of a diagram, okay. And you have a memory, small memory available in the microcontroller. This memory address register holds some kind of a address, and then one can address this memory, okay. Something is there. Then you have some this is only adder here. So this adder is taking value in the register T and value in the register AL, and this is adding together, and this value is available in this register. And when you put this output enable pin high for this register, then that added value will be available on the data bus, things like that. So you can have only this one way kind of a direction coming, the data is coming on this data bus, you cannot write in this register otherwise, okay. Like that some kind of understanding can be built for by reading such a kind of a diagrams. Similarly, you will find these kind of diagrams in many modern kind of a microcontroller data sheets, and one needs to kind of figure out, have ability to figure out what these diagrams really mean. So that can be done now with this understanding that we have done so far, and by reading the data sheet of that microcontroller. Okay, so let's proceed with some operations here now, okay. So this is our understanding of this microprocessor, and suppose we connect now some signals like same S1, S2, S3, S4 in this fashion, okay. And I tell you, okay, now can you just guess for such a kind of a diagram what is the operation that will be happening, okay. So read this carefully, like how this S1, S2, S3, S4 are connected to this, and they are going in the same sequence high, okay. So S1 will go high first, then S2, then S3, and then S4, okay. So you can pause here for a while and figure out, like a little bit at least, to think about, okay, what will happen in S1 sequence, for example, what will happen in S2 when S2 goes high. So like that you can think, and then you can proceed. We'll go one by one in the understanding, okay. So let's say S1 goes high, okay. So when S1 goes high, the contents of this register MA, okay, which are always there on the so see, this has no output enable, nothing. So this is always connected to this memory. So contents of memory register, this memory address holding register will be available on the address bus there, that is there for always. Then when S1, S2 goes high, this S1 goes high in this thing, then this chip select will happen here, and this memory will be selected, okay. Now this memory is getting selected, and then the data from this will be available on the so the data from this will be available on the data bus. Okay, so which data is available? Data which is at a location which is governed by this address here, that data will be available on the data bus. Okay, then what else is happening? That data is this is right here. Okay, so when S1 goes high, that data is also getting written in the register T. Okay, so the data will be fetched from the memory location and it is given to the register T. So there is a clock that is kept here. Okay, to make sure that this clock signal is given along with S1. So S1, you remember, it is half. This S1 goes high for a full clock cycle, and this, when it is ANDed with the clock, this output will be only half cycle up. Okay, this is done to kind of make sure there is no clash of the data, or the write operation is completed well before, like this the data gets invalid on the data bus, so that there is no clash of the data. So some nitty-gritties of that sort are done, which you don't need to really bother about. Okay, so now let's see what is happening in S2. Okay, so that's what we saw. Why do we need AND gate here? And then yeah, so now when S2 goes high, you can see S2 is here and S2 is here. Okay, what is happening here is again something is getting written here. Okay, what is getting written? So see, this is output enable for this A register, so that is going high. This is OR gate that is going high. That means data from register A will be available on the data bus now. Okay, so you see the data bus is same data bus is shared in all different registers and memory and so on and so forth. Okay, so the data from A will be available on the data bus, and it is written in which register? Now it is written in the AL register. Okay, that is happening in the second part of the sequence S2. Okay, so you remember the first part, the data from the memory was available here and was transferred here. Now in the second part, like the data from the register A is going to get transferred here. Then what will happen in 3? S3 goes high, you see that this data from this is now added together. This is the data which is data in the register T plus AL will be added together, and that data will be available now on the data bus. Okay, now which register that data is written? That data is written in register A again. So whatever was previous content, it is overwritten, and like that addition will be available here. Okay, now that is what is done here. And then what is happening in the S4 sequence? You take this data which is from S4 register. Now it is put again on the data bus, and in S4 it is now write enabled, and like that data is returned to this memory. Okay, so so this is how, like typically you can see that the sequence of operations is going to happen. There are some nitty-gritties that we need to figure out and things like that, but this is giving you some kind of a sense of, okay, oh, this is how, like some things connected together, these some operations can be performed. And we know that these operations are has not great meaning here. Okay, so one can have the summary of these operations which are achieved in different state, but you can see that, okay, this some kind of a successive addition is performed here on some data, but it's not a greatly meaningful kind of a thing. Okay, and also suppose we have this microprocessor, this will be only doing this. There is no other command that is to be, we cannot write any command that's saying that, okay, oh, this is my program, and I want to have like something done like that, or I want to have some instruction set which will control this kind of operation. Nothing like that is there right now. Okay, so we want now to have such a kind of a facility. We build some more stuff in the thing. Okay, so we add some more registers to our primitive microprocessor and look at some more operations with this microprocessor too. Okay, so this is a microprocessor which is having now a lot more number of registers, but still that additional ALU is there. So there can be many different logic elements that can be used in ALU to arithmetic logic unit to kind of perform many different operations. One can now guess that this is very easy to see that okay, we can have a lot of things put together in our ALU. You can have some counter or other kind of things also put as a part of this microprocessor unit. So now what we need to introduce here is we have notice here we have introduced some register called PC register. This is like a program counter register. Okay, so this will keep track of which instruction you are running at present. Okay, so you have some sequence of instructions that are typically written as a program. That's what you write when you write a program, right? You write some first command line, second command line, like that you write this, and one after other they get executed. Okay, so this program counter register is a special register which will keep track of that count. Okay, that it will fetch the instruction first, whatever that you have written that program, it will fetch that instruction and it will put that into instruction register is other kind of facility that is there. This is a special register. So there are all some special registers having some special functionalities. Okay, in the microprocessor. So typically you will have this kind of not all registers can be accessed by a user. This is a very typical for any microprocessor. You can address, say for example, this program counter register, you cannot write anything into that. Okay, you can just read from the program counter register to see. Like that you will have in every microprocessor some kind of special registers will be there, and every registers will have some functionality, and that functionality will be written in the part of the data sheet. You don't need to guess from just this diagram. The diagram helps you to kind of guess some of the aspects, but the rest of the thing can be read from the read from the data sheet of the microprocessor. So there is this other kind of a register which is typically will be there now. It will have this memory address holding register. From that register, that address can come on the address bus, and that particular location in the memory will get addressed. Okay, so this is some kind of a description or understanding of this diagram. Okay, so you can pause it and read through and understand a little better if at all you need to be. So now there are some questions that we can raise now. Okay, so these are like some kind of a special registers, and how these registers would work is what is gotten here. So we don't worry about. So what we want here is special functionality to this register. We want the data from the data bus transferred to MA. Okay, so some data from the data bus can be transferred to this register. Okay, but you cannot read and transfer any data from this register back to the data bus. Okay, and that data will be transferred to the address bus when the output enable is so this functionality is needed. Can you guess why this functionality is needed? See, we have written some kind of a program and some memory locations. Okay, so when we execute, we need to give microprocessor a location from where you want to execute. That location, when you give, that location will be the starting point for this memory address register to hold. Okay, and that address will be there on the address bus, and then that address can be transferred to the address bus, and then your address bus is pointing to that particular location where your program is written in memory. And now that first command that you have written the program, that can be now fetched from this data bus, fetched from this memory and gotten onto the data bus and transferred to this instruction register. Okay, IR. These are the so these registers you will typically not see for the user to be accessed. Okay, so yeah, we are giving this here to just to give you some glimpse of how things are happening inside. Okay, so this register you will not be able to see, or many times they will not even kind of put them in the architecture. Okay, because the user is not concerned with those registers too much. Okay, so now the question is, we would like to have this facility, okay, to code or program, and that say some instructions are written some memory locations, and we would like to have these instructions to be fetched, as I said, from the memory and given to this register IR, and now from IR, like they will be taken and executed in some way. Okay, so let us see that how things happen a little bit in more detail. The say program counter is holding first memory location, and so this program counter, if you see, is maybe here you can see. So program counter is holding that first memory location. Okay, so that program counter will be now holding the starting point. Okay, that starting point address will be transferred to the data bus. From there it should be getting to the memory address register, and then it will be available on the address bus. The moment this is executed, then second address, so this program counter will update it increment by 1, and then second memory address will be there here. Then again it will be taken here, from here it will be transferred to this, and again it will be executed, or this it is be addressed, and then the second line of your command, okay, or program will be second command of your program will be transferred to the instruction register, and then it is executed. Like that, this sequence will continue further. Okay, so now we will now create this kind of a brief notion for the instruction. So PC to MA. Okay, what it means, like contents of this register PC are transferred to MA. So for that, lot of operations are to be done. Okay, before, so the way we said, okay, external location, some some data hold in external location to be transferred to the memory. Now this is just a transfer from one memory one register to other register. There is no memory involved here. Okay, so program counter transfers some data to memory register. Okay, so we now see that, okay, this other instruction that we want to see, the memory address will be given by this program counter register, which is now holding the memory address, that is pointing to some memory location, and the data from that memory location needs to be fetched and transferred to the IR register. So this will indicate briefly as M is stands for memory, which is pointed by this memory address register. That particular kind of a location, whatever is there, is to be transferred to IR register. Okay, this is how we represent these small commands. And then PC is incremented. Okay, so program counter needs to get incremented. Okay, so these are like small briefly we write these commands. Okay, and now we don't worry about how this will happen actually. So let us kind of skip through this part, how the program counter is function to do some things that are described. Okay, so let us not worry about this part here. This is more like how do you digital circuit we will design about that. Okay, so these are more details about how the program counter is made to function the way it is there. Okay, so these are the operations that we said it should happen. So program counter content should go to memory address register, and then whatever is addressed by that register to the memory, that location of the memory, contents of that location in the memory we transfer to IR register, and then we update. This is the sequence of operations should happen every single command that we execute. Okay, So irrespective of any additional operations that are to be done. Okay, and then we can have these additional operations that move B to A, or some kind of operations that we can add to this sequence. Okay, and now we want this thing to be executed in some kind of a way that by using this some kind of combination of the states, or combination of the some of these each of these can be designated as a state. Okay, so we'll see how this operation can be executed in a so this is a example of another kind of a command. Okay, so this is so these three are common, and then now contents of A are to be transferred to AL register, contents of B are to be transferred to the T register, and A should again hold the addition of AL and T, which is given by ALU, arithmetic logic unit. So this is another command that we have built up. Okay, so we are kind of building these commands now. Okay, this is command 1, where like this just moving of contents of A from register A to B happens, and then like there is a second command. Okay, so we want to see like how these commands can be finally executed. Okay, so we create this kind of a table in which like we have these commands which are now called mnemonic. Okay, so these are like a assembly language kind of a commands. Okay, so typically this is a way, this is a syntax that will be used in the assembly language for moving some data from one register to other register, add something to the register, like that you will have these different kind of commands that will be possible. Okay, so say for this first command we want like this this is a like micro instructions that are called. So whatever this we say, okay, PC to MA, this is a micro instruction. So these micro instructions are typically which can be completed in one kind of a clock cycle. Okay, and you have like second instruction, say micro instruction, third micro instruction, like that 3 micro instructions are required for executing this one single command. Okay, so this is your command, and then there will be some code associated with that command. Okay, so we don't need to worry about this code here. Okay, this code will be used by this IR register to actually execute this sequence of things, and how that happens we'll get some glimpse of it, but we'll not get into too many details about it. Okay, so these are the 3 kind of operations to be happening one after other for a first command. Like that you can have the second command operations. Okay, and the what it does here, result, and its code. So typically these are the things involved in every of your instruction set. So this assembly language is one of the fundamental kind of a language for the instruction. Your each microcontroller will have its own instruction set, and it will produce some kind of instructions or some commands, it will be mentioned there, and these commands will get executed by using this kind of a micro instructions typically. Okay, so we are just getting a small glimpse of that. Okay, so this is a second command that we have generated, then some kind of a third command I'm generating here. So we will not get into too many details about how these commands are, what are these operations and things like that. What we want to see is that every command that, or every instruction that is issued in microcontroller or microprocessor will have this some set of micro instructions to be executed, and they are executed by using some kind of a timing and control unit. Okay, so all these micro instructions together, you can see that we want now only like we'll add this S1, S2, S3 we have said here, but S1 and S2 are common because these micro instructions are common, but S4, S5, S6 are new kind of a micro instructions. Like that you'll identify like every command, whatever you want to want the operations to happen for that command, we will add these micro instructions to the set, and all these micro instructions form like this distinct kind of operations that are to be performed. And now these operations can be say up to here when we come, there are 11 kind of states that we get distinctly here. Okay, So these 11 things, these are like, remember, these are to be executed in one clock cycle kind of a thing, the way we had executed S1, S2, S3, S4 in our previous example. The same way this will happen now. The logic will be little more complicated and more involved. Okay, so we'll just get a small glimpse of that. So these are like 11 kind of a distinct operations which are kind of called the states here. And now we want to have these states executed in a one particular kind of a way when command 1 or command 2 is issued. Okay, so we have these 4 commands that are defined for this microcontroller, and we want to execute whatever commands that is written by the programmer. Okay, so but then when this command is issued, then this operation should happen, is what we want to make sure. So we start generating a state diagram which is now dependent upon the instructions that are there, 4 instructions that we have. So S0, S1, S2 will be instructed, it will be executed anyhow. Okay, then S3 will be done only when the command issued has some particular format, or this is a command which is having code 00. Okay, so we start drawing this kind of a state diagram from here, saying that okay, S1, S2, S3 are same states. I'll go from S0 to S1 to S2, and then I'll go to S3 only when IR is equal to something. Okay, like that we'll start drawing the complete state diagram, and then we will start connecting the signals. Okay, so this signal connection again can be seen in a way that you want to have these operations to be done. Okay, so this is kind of very easy, as similar to what our previous example. Okay, so we have the signal connections, the states identified, and for each of the states now we will do this kind of a signals connection to do this task. Okay, so now whenever this S1 S0 goes high, this part will happen. When S2 goes high, for example, this part will happen. Okay, that is going to happen. You can check it here. Okay, so one can construct that very easily. And then what we want here is now the state diagram to be generated for these instructions to happen. Okay, so say for example S2, when this happens, like this S2 is here, S2 is here, S2 is here, you can see that this will get executed when S2 is going high. Okay, so what we have done is so far is identified these states, and each of the states when it is to be executed, what is to go high and low in this connection we have done. And now we will see what is how it is to be executed. Okay, so for that we saw we will use this kind of a timing and control unit here. So we had previous unit which has simply to go through S1, S2, S3, S4, that's it. But now here we want to have this control given by this IR register, as I was saying before, that okay, S1, S2, S0, S1, S2 are executed anyhow, but S3 we should go only when IR has something. Okay, IR. So we start writing it as a state diagram. Okay, you remember our sequential logic we developed by using state diagram. So this is how we develop this diagram. Okay, so when IR is this, from 2 you go to 3. Okay, and then you go back from otherwise if with IR if is something else, you go through these different states. Then again you have some kind of a way. This is you get this sequential logic diagram done, and then you can execute this logic by using your so each of these states will have one D flip-flop selected, and we can start connecting things together, and we add on with the D flip-flops some more kind of logic elements to get this executed. So I will not get into details of that again. We will just directly see the final result here. Okay, so you can pause and go through some of these things more detail if you want to later. Okay, so this is how this final circuit is going to look like. Okay, so this we generate depending upon instruction. We decode the instruction and get say these pins high, and when these pins are high, then the sequence of operation is going to run according to the state diagram that we have seen. Okay, so this is like a complete picture of the stuff. Okay, this is not typically you will not get to see this in the microprocessor datasheet. What you will see is only the architecture, that okay, this has these registers and these registers have this functionality. How it happens, you don't have to bother about. So this is like a complete picture of a typical microcontroller execution, operation execution that happens in the microcontroller. And of course there will be then a lot of other facilities. You can have additional registers put together for getting these for loops, while loops, and then storing something for temporary, that stack and other kind of registers can be introduced. So once you have this base understanding of how things are happening, then all the other things can be imagined very nicely, how they would have been happening there. Okay, so so this is just a summary of this whole thing, whole process of this 4 lectures on microprocessor that we have done to get all the basics very nicely understood here. And this understanding will help you read through the data sheets of microprocessor very easily. So we have these instructions. These are called typically assembly language instructions. Okay, and each of these instructions will consist of several micro instructions, and each micro instructions will tell you, okay, that much time will be taken for. So if you have 3 micro instructions to run these, then 3 clock cycles will be needed to execute these. So you can get also some sense of how much time will be taken to execute my command. Okay, and this machine language or assembly language is what is called, this instruction set is termed as. Okay, and this is how, like, see, you write a program in C or any other language, it is getting, when it compiles, okay, what that compiler does is basically converts all your higher language stuff into this assembly language instructions, and then executes that assembly language instruction the way we saw they get executed by using the timing and control unit. Okay, so that's how, like, things happen typically in the microprocessor. Okay, so we'll stop here for now.